The first time that I heard about the Kalman filter, it sounded like one of those mystical algorithms that people throw around in robotics or aerospace. Like it's this magical thing that somehow knows where you are, even when your sensors are technically lying. But once I started digging into it and using it in real projects, I realized it's not magic at all. It's actually one of the most beautifully simple ideas in engineering. It's just about how you combine what you believe with what you observe. And in today's video, I'm going to show you what that really means. Let's start with a problem. Imagine you're flying a plane. You have a few instruments telling you your altitude, like maybe a barometer, a radar, and a GPS. Now, none of those are perfect. The barometer might slowly drift from the true readings, the radar might have noise, and the GPS might lag a bit. So, which one do you actually trust? Initially, we all used to think that we could just take the average with maybe some filtering, like the moving average filter, to get the best value. But that doesn't really solve it, right? Because each sensor is wrong in its own way. Averaging them would just give you a blurred version of what might or might not be the truth. What we really want is to somehow see through the noise and figure out what the actual altitude probably is. And that's exactly the problem that the Kalman filter was designed to solve. Let's try to get some intuition by taking a simpler example. Imagine you're tracking a car moving in a straight line. You know its current position and roughly how fast it's going. Even if you don't get any new measurements for a second, you can still predict where it's likely to be next, just by using the equations of motion where position is equal to the old position plus velocity into time, or any of the kinematic equations. That would simply be a prediction. Now, when a new sensor reading comes in, maybe from your GPS, you know that the reading has some noise. So instead of just replacing your prediction with that value, you combine them. You trust both, but not equally. If your prediction was pretty solid and your GPS is noisy, you lean more towards your prediction. But if your prediction was uncertain and the GPS seems reliable, you lean more towards the GPS. This balancing act between what you predict and what you measure is the essence of the Kalman filter. Under the hood, it's doing something really smart. It's not just blending numbers randomly, it's mathematically finding the best possible estimate, which will be the one that minimizes the total uncertainty. In more formal terms, it's minimizing the error variance, which might sound intimidating, but it basically means that it's figuring out the most likely true value given everything you know so far and how uncertain each piece of information is. If you imagine plotting that uncertainty, it's like having a curve that shows where the truth could be. The Kalman filter keeps adjusting that curve every time new data comes in. It narrows it, shifts it, and gives you the peak, which is the point that's most likely correct. And using this process, we're not only able to get a number, but also figure out how confident we are about that particular estimate. So we actually know how much we can trust the output of our filter. And that's what makes it so powerful. It doesn't just estimate, it also quantifies belief. Now, some of you might be wondering, if we already know the equations of motion, like position equals velocity into time and all of that, then can't we just calculate everything directly? And that is a fair question. But the issue is that real world systems never behave exactly like our equations. There's always something missing: wind gusts, friction changes, sensor drift, random noise, or as always, the ignored air resistance. So, what the Kalman filter does is say, okay, let's start with a rough model of how we think the system behaves. And then it continuously corrects that model using actual measurements. It's like driving in fog with only your headlights. You can't see everything perfectly, But based on the tiny amount of road ahead of you, you can keep correcting your steering as you move. So the model gives you the approximate direction, and the measurement ensures that you stay on track. So obviously, it's reasonable to wonder, what if we don't have a model at all? What if we genuinely just have no idea about how the system behaves? In that case, the standard Kalman filter can't really help, because it relies on at least some idea of how the system changes from one moment to the next. But there are more advanced versions, like the extended Kalman filter, the unscented Kalman filter, or particle filters, that try to handle more chaotic or nonlinear systems. Maybe we could do a future decoding video specifically for how those algorithms work. But essentially, even for them, the principle stays the same. You still predict, you still correct, but you do it with different mathematical tools. A lot of this might sound fairly difficult to implement, but it's really simple with modern coding. A Kalman filter in code actually looks surprisingly simple. Something like this: while true, predict, and then update. That's it. Those two steps, predict and update, keep running forever. But inside them, you've got a lot of linear algebra quietly keeping track of how uncertain everything is, and how much each piece of information should influence your next guess. A lot of how the system behaves is also calculated in the form of matrices and linear algebra, specifically in something called the state space model, which can be linearized and discretized and so on. But that's slightly beyond the scope of today's video. But maybe another one in the future if all of you want to dive right into the math. So the Kalman filter is basically a real-time form of Bayesian thinking, where we constantly update our belief about what's true based on new evidence. The funny thing is, once you understand this, you start noticing the Kalman filter everywhere. In GPS systems to blend satellite data with accelerometer readings, in your phone camera stabilizing the image by predicting how your hand will move, in robots, drones, and even self-driving cars. All of them use some form of this idea to stay grounded in this noisy world. It's the quiet math that makes machines aware of their surroundings and also makes us realize why we needed to study those simple equations that don't work well in the real world, where we can't just ignore air resistance. When I first learned it in my master's course, I thought it was just some filtering algorithm. But as I worked with it, I realized it's not about filtering at all. It's about trust, deciding how much to believe your model and how much to believe your measurements. And that's a beautiful way to think about the world too. We all have models, ways we think things should behave. And then there's reality, constantly throwing noise at us. The trick isn't to pick one, but it's to combine both intelligently. And that's essentially what the Kalman filter does. It's how machines think clearly in a messy world. And honestly, that's what makes it so elegant. I hope this video helped decode the Kalman filter for you, and if you liked what you saw, please consider subscribing, because there's a lot more to decode. Until the next video comes out, thank you so much for watching, and don't forget to stay curious.